Good day everyone. Today I'll present our research titled Exploring Yolo Architecture for Detection of Ukrainian Car License Plates in Images. Our research aimed at evaluating different generations of Yolo models specifically to detect Ukrainian vehicle license plates. We wanted to find out which version of the Yolo architecture would give us the best balance of accuracy, speed, and reliability. Additionally, we tested these models thoroughly across various real-world scenarios, including Cyrillic plates, electric vehicle plates, American-style plates, and challenging conditions like poor lighting, angled views, and unusual plate placements. Yolo stands for You Only Look Once and is recognized widely for its excellent real-time object detection capabilities. The strength of Yolo lies in its ability to detect objects quickly in a single pass through the neural network. Its architecture includes a feature extraction component known as the backbone, a neck that aggregates features to improve multiscale detection, and a head responsible for predicting bounding boxes, object classes, and confidence scores. To objectively compare different Yolo models, we relied on critical metrics widely accepted in machine learning: precision, recall, mean average precision at a standard intersection over union threshold of 0.5, and mean average precision averaged across IOU thresholds from 0.5 to 0.95. To provide a single unified evaluation score, we combined these metrics into a weighted measure called fitness. This fitness score emphasizes overall model quality by assigning specific weights that prioritize detection accuracy, particularly under more challenging scenarios. We carefully selected these weights, giving higher importance to the MAP50-95 metric, which reflects the model's ability to consistently detect objects accurately even when bounding boxes vary slightly from the ideal position. In our study, we selected specific weights for each metric to emphasize consistent detection accuracy, precision, and recall. Each received weights of 0.1, MAP50 a weight of 0.3, and MAP50-95, the most critical measure of consistent accuracy, a weight of 0.5. For our research, we collected approximately 11,500 images of Ukrainian cars from open online sources. To accurately identify the license plates, we annotated each image using the CVAT annotation tool, labeling the plates clearly with bounding boxes and assigning a uniform class identifier. The dataset was divided into training and testing subsets, with 10,000 images used for training and the remaining 1,500 reserved for evaluating model performance. The training involved running each Yolo model through 100 epochs, applying consistent settings across all models, such as a batch size of 16, an input image resolution of 640x640 pixels, and the Atom Optimizer. The computational setup included an Intel i5-14600KF processor and NVIDIA RTX 4070 graphics card to ensure reliable, efficient training. When detecting license plates in new images, our trained Yolo models perform a three-stage prediction process. Initially, input images are resized to match the network's required input dimensions. The neural network then predicts potential bounding boxes along with confidence scores. Finally, these predicted boxes are rescaled and accurately mapped onto the original images, providing precise and practical detection outcomes. When evaluating the Yolo model's performance, we observed that Yolo 9 achieved the most favorable balance between detection accuracy and speed. This makes Yolo 9 particularly suitable for applications requiring real-time detection. Although Yolo 11 showed strong accuracy, it was slower and struggled more noticeably under complex or challenging conditions. We conducted the first experiment to evaluate how effectively each Yolo model identifies different types of Ukrainian license plates. Specifically, we selected images with green plates for electric vehicles, plates containing Cyrillic characters, and American-style license plates. These plate variations represent practical complexities that any real-world system would need to address, such as different fonts, colors, and layouts, all of which could influence detection accuracy. Our tests demonstrated that all Yolo versions provided generally reliable and accurate detections, closely matching the actual positions of the license plates in standard scenarios. The bounding box coordinates predicted by most models were nearly identical to the ground truth. However, Yolo 11 showed some notable deviations, particularly under angled views or unusual lighting conditions. This inconsistency highlights areas for further optimization and reinforces Yolo 9 as a better choice, offering a consistent performance across varied plate types. In the second experiment, we deliberately tested the Yolo models under more demanding and realistic scenarios, where automatic detection typically faces greater difficulties. We selected images featuring license plates viewed at sharp angles, captured under poor lighting conditions, or located in non-standard positions. These scenarios represent common real-world challenges that any practical detection system would regularly encounter, thus providing an essential robustness test for the models. The results reaffirmed the overall robustness of most Yolo models in handling difficult detection scenarios, with minor errors attributable mostly to challenging angles or poor lighting. However, Yolo 11 consistently showed greater inaccuracies, especially in bounding box dimensions, indicating reduced reliability in complex situations. This second round of testing solidified Yolo 9's position as the preferred model for real-world applications, as it delivered consistently accurate and stable results even under the challenging conditions presented. Based on our extensive testing and evaluation, we identified Yolo 9 as the optimal model for detecting Ukrainian car license plates. It offers the best trade-off between processing speed and accuracy, proving particularly effective for real-time scenarios. While our results confirm that Yolo models are generally robust, certain challenges remain, especially under poor lighting, angled views, or unusual plate positioning. Going forward, our research will aim to improve the model's adaptability to these challenging scenarios and integrate this technology into practical surveillance and traffic monitoring systems.